Hi all. So till now we have studied about the analysis of cooling of land body, and we have derived the relation for the temperature variation with respect to time, and the relation was like this: T minus T infinity divided by T naught minus T infinity equals to e power minus HAST divided by MC. Okay, so if we write like T is equal to T infinity plus T naught minus T infinity times e power minus HAST divided by MC, right? So temperature is function of time only. That's why lumped body, right, means temperature is not varying with respect to location. All right. And we have also seen that how temperature exponentially vary with respect to time for both cooling and heating cases. And if we look closely, this ratio here, HAST divided by MC, which is nothing but the ability of the medium to convect from the surface to the ability of the medium to store thermal energy. So these terms are relating to the storage of thermal energy, and the numerator is denoting the convection from the surface of the body. All right. And one more thing, that this ratio is non-dimensional. All right. So it means the right hand side must also be non-dimensional. This can be possible when this term is non-dimensional. All right. It means MC divided by HAS must have the unit of time. You can cross check it by putting the units of mass as kg, C as joule per kg Kelvin, and heat transfer coefficient as watt per meter square Kelvin, and the surface area as we all know meter square. Okay. So this thing MC by HAS is nothing but the time constant. Okay, thermal time constant. Thermal time constant. It is the time which is taken by the body to reach this temperature difference as the 36.7% of initial temperature difference. It means if you put the small t as T star, we will get this ratio as e power minus 1, which is nothing but 0.367. All right. Okay. So for the body to respond faster thermally, or faster thermal response of the body, we should have this time constant should be as low as possible, which can be possible. So we can write like for faster thermal response, the ratio T minus, sorry, this ratio mc by HAS, which is nothing but thermal time constant, should be as low as possible. And it can be as low as possible when body has less density, which is also dependent on volume and density. When the body has less density, small size means small volume, so mass is small. Second point, when the body has less storage capacity for thermal energy, and when body is kept in the medium which has a very high heat transfer coefficient and surface area of the body is large. Okay, so this is all about the thermal time constant. So now we will look at the further analysis of this lumped capacity, lumped body. So if we want to, so we have this relation, right? This relation, and suppose we want to find the instantaneous rate of cooling, means at what rate the temperature is changing of the lumped body. So how to find that? So this is nothing but instantaneous rate of cooling of the body. Alright, which is nothing but T as T infinity plus T naught minus T infinity times e power minus HAST divided by MC. Alright, so to find the rate of cooling, means temperature gradient, just derive this, differentiate this equation with respect to time. T naught is constant, so we will have T naught minus T infinity times e power minus HAST divided by MC. And for e power ax, we know from our school level mathematics that its derivative is e power ax times derivative of ax, which is nothing but a. So we will have e power ax times, we are derivating with respect to t, so we have HAS divided by MC. Alright, so this is the instantaneous rate of cooling. So if we want to find the cooling rate at particular time, we can find it by plugging it at this particular value of T. If we want to find that what is the cooling rate at initially, means when the body starts to cool, so that is called the initial rate of cooling. So initial rate of cooling when T is equal to 0. So if we put the T as 0, so we will have T naught minus T infinity times minus HAS divided by MC times e power 0, which is nothing but 1, and we get T naught minus T infinity times minus HAS divided by MC. So initial rate of cooling is depending on the initial temperature difference between the body and the surrounding, and also on the material properties and heat transfer coefficient and the size of the body. All right, so next we want to find the instantaneous rate of heat transfer from the body. All right, means let's say the body was at initial temperature T at every point, and after time T the body has temperature some T. So we want to find that how much heat transfer is happening from the body when it is placed in the surrounding having heat transfer coefficient H and free stream temperature as T infinity. All right, so that is called instantaneous rate of heat transfer, which is a function of T. All right, so which is nothing but H times AS times T minus T infinity. So if we go term by term, which term is a function of time? H is not function of time. HAS is also not function of time. Alright, this area, how can it be? T infinity is also not function of time, but T is function of time, right? Because for lumped body we are having this relation. So if you will plug in this value of T here, you can get the instantaneous rate of cooling, instantaneous rate of heat transfer. And if you want that how much total energy is transferred from initially to the at a particular time, so you can integrate this relation to that particular time. Okay, so if you want total energy transferred in joules, of course, so we can get by integrating this Q as a function of time with respect to dt from 0 to t, so which is nothing but h times as times t minus t infinity times dt 0 to t minus t infinity. We know that it is nothing but t naught minus t infinity times e power minus hast divided by mc times dt 0 to t. So its unit is joule. Alright, so if you integrate and rearrange, you will get mc minus mc times t naught minus t infinity times e power minus hast divided by mc minus 1 in joules. Alright, so that is all about the lumped heat capacity method. So we will look further in this in the next class. Thank you.